All right. Welcome back. Can you hear me okay? Everybody, I think so. If you can't hear me, let me know. Okay, so a couple things. Number one, I sent a note. Hybrid class next couple weeks. I just noted the number of people had told me they were not feeling well. I wasn't trying to pick on any of you. You're welcome to be here. Whatever, we can make this work. I just wanted to give everybody the option and just be realistically. I wanted to have more time when we would do more coding activities together this semester. That never really came through. So that was the reason for not doing a hybrid class in the first place. Like, well, the next couple weeks we're not going to have coding. Why should I force you all to be here? But thank you for coming. Thank you for being on Zoom. I'm thankful for YouTube. Just like Thanksgiving extended this week. Let me tell you what I'm thankful for. I'm thankful for you for listening. So that's number one. You have your course evaluation. I sent that email. Number two. So please take the time, if you will, if you spare me a few minutes to evaluate the course, it'd be great. Again, I personally, I don't want you to disregard anything on the form, but I personally pay most attention to the written statements. Like if you didn't like class and rate it low, I get the number, but it's kind of like, yeah, what didn't you like? Or if you did like class, but things weren't exactly perfect, which they never are, especially when I teach, let me know. Let me know what I can do to fix it, make it better. I'd like this multidimensional class to be something in the rotation to make sure I get it right. There's a lot. I wanted to put everything in this class this year, and that was just not going to work. So, okay. Let me just double check. One other thing. Once again, I mentioned before there was no more formative assessments, so you can forget about that. Homework 6 is due like next week, I think it is. Yeah, it's not this week, it's next week. So you've got time for that. And then there's the 10-minute final, which I'm going to have. Well, I gave you the details for it. It's just going to be a little scenario talk to me about it. It's going to go quickly. 10 minutes is not a lot of time, so don't worry about it. And you know, I'm not here playing gotcha. I'm not here to try to trick you. At this point in the ballgame, at this point in your academic careers, like grades, really do they make a difference? It's more, what do you want to learn and why are you going to use it, right? And I struggle with this because it's like, when preparing a class, particularly graduate class, there's always the approach. Like, I can force you to do work, right? I'd be like, oh, we're going to do homework, it's going to do next week. And I like that. But at the same time, I'm not, I feel like that's sort of weird. I feel like your own personal motivation trumps everything. I might go back to that after the semester. Like, you take what you get from this class. You just need the grade, fine. What do I care? Right? But those of you who work hard, which is everybody in this class, I believe, aren't going to worry about that anyway. So what do I worry about? All right, that's all. I had a question in chat. I mentioned referencing reading for the final. Are you allowed to bring any notes? Yes, you can bring anything to the final. I don't care. Completely open notes. Bring a library. I don't care. How's that sound? That work? Cool. Notes, open notes, open book. I don't care. Remember, you have 10 minutes, so I'll ask a question. You'll conjecture something. I'll say, but what about? Have you thought about this? And that's where we'll go. That's how I envision it. Okay. That's all. And by the way, the questions I'm going to ask, the scenarios I'm going to ask are ones I think that are going to be pulled from my life. Okay. I found this. What would you do in that situation? Okay, great. Let me think about that. Okay. And again, there's only 10 minutes. So yes. Bring the Library of Congress. I don't care. You can search it in 10 minutes. Although, if you bring ChatGPT, I imagine I will be able to eliminate it. I read a grant proposal last week. I'm pretty sure half of it was written by ChatGPT based on how excited it was with its superlatives. This model does a remarkable job. I have written about a lot of models. Never once have I said any of them do a remarkable job. Remarkable is editorial. Doesn't need it, right? Okay. Any questions on final stuff like that? Great. All right. Finally, one thing I did want to bring up was the last homework question number 4. The one where I gave you M+ code and said, what's the model? Let's talk about it a little bit, because that was one that I think was difficult. I'm going to grab the question real quick. Just so I have it all together. Give me just a moment. It's coming, I promise. Okay. Oh, no. Let's do that. Right here. Here we go. Can you see that? Okay. So this model right here. Anybody want to try to name it first? Let's take a look. What are the clues about naming? First, analysis type equals mixture. So it's some type of mixture model. Of the mixture models we discussed in class, we had latent class analysis, mixture IRT, etc. Right? So we got one of those. That's the ballpark. So the name of it, we need to go a little bit deeper into what's happening in the model itself. So now let's take a look at the overall statement. That by is a clue, right? That indicates, if we just had this as a model, the highlighted statement, we would be in a measurement model of some sort, psychometric model of some sort, right? Where F is the latent variable, and U1 through U8 are its observed indicators, or the things that measure F. Right? So we have two classes. We know the overall model is some type of measurement model where the mean of F is set to 0. And then when we go into each class, we can tell that here we see the F statement repeated. Now we have another additional factor in that the very first loading in class 1 is set to 1. That's what the at1 means. So the loading for class 1 is set to 1. So we're able to estimate F's variance in class 1. Right? And then this is the set of thresholds for M+. So each of the items is binary. Actually, we don't know that here. I should have said that we don't. The first threshold, binary items have one threshold. There's always $1. If you have 3 category items, polytomous items, you'd have one threshold fewer than the number of categories you have, right? So here, in this case, by indicating that we want the thresholds estimated, this is telling us that class 1's threshold will be unique to that item. Okay? And then class 2, let's take a look at how it varies. Again, F by, the very first factor's loading is set to 1. So this, again, would be another measurement model. But apart from that first factor loading, we can see that the loadings for each of the other items, or the discriminations, whatever you call that parameter, are going to be estimated separately in class 1 versus class 2. Does that make sense so far? You all have that taken care of. This is another thing. Everybody's looking like you're bored. You bored? Okay. I guess some high school students here we would talk to if you're really bored. It's cool. By the way, if I didn't say it, thank you both for representing our program at open house. Again, we're estimating a variance. This variance will be different from the variance in class 1. And again, we're estimating separate loadings for each. So now, what do we know about this model? We know it's a mixture model. We know within each class there's some type of measurement component. So at this point, I would call it a mixture item, IRT model, or mixture QTL. That's the name I'm giving it. Mixture IRT, mixture QTL. Because basically you're saying, I've got an IRT model in each. Yes, I'm using not the standardized factor for estimation. If I just had class 1 here, this would be a legitimate, if class 1, this was just the model, this would be a legitimate measurement model, right? An 8-item, one factor analysis, one factor model, and because these are categorical, I call this an IRT model. Anybody disagree on that? We want to talk about that more. All right, now how do we notate this thing? That's a harder part. But let's think about how we do that, okay? So, I didn't give you much guidance on this. I was just hoping that you'd try putting some things down. And I will say the mixture model notation, if you look at the mixture model field, I remember just being bewildered. I think that's a good word. Bewildered by it back when I was in grad school, because it seemed like they were confusing conditional versus marginal in some of what they do. So I'm going to try to not bewilder it, but let's think of it this way. What we want to talk about is the probability an item represents y. Actually, we call them all u there, right? So what do we call this u? Some u sub I for a person, an item, equals 1. But let's make this conditional on theta for that person and the class of that person. Okay? So this is now a conditional item response probability, just one of them. Everybody with me so far? You know what this is? This is, in this case, what we're going to do, m plus uses thresholds, right? You know the difference between the intercept and the threshold. That's right. An intercept is negative 1 times the threshold in this case, right? One is modeling the probability of 0, the threshold, and the intercept is modeling the probability of 1. So here in this case, to really do the threshold, I would call this lambda for the item times theta for the person minus the threshold for the item. That is how that might work. Does that make sense? To you? Do I have Zoom open? Sure, I hope so. There it is. Sorry. I've forgotten my 2-monitor layout for all this. So relearning the hard way. All right, so we have that. This is over 1 plus ASP of lambda I theta p minus tau I. Right. So that's your. That could be the notation for it. I'd be fine if that were what you put down. But there's other ways of putting it too, because a lot of you tried to put this into the mixture model notation. So let's go there, right? So this is, we're going to call this is like IRT world, or another way of putting this is, the key in this is right here. This is conditional, right? This is a conditional probability. If we knew a theta and we knew a class, we could plug in that class's item response. Oh, this is not correct. Dang it. Why is this not correct? Because the loadings and the thresholds are class specific, with the exception of the very first one, when we can just say that lambda 1 equals lambda 1 2 equals 1. Right. The first threshold, the first loading of each of the first. Item 1's loading for each class is equal to 1, and they're both equal to 1. So that's the one constraint. So this right here. Stay there. Right? So far, okay? Okay. But let's look at this as a mixture model notation. Now, you remember the mixture model notation I wrote. If I can write a latent class model down, let me do that real quick. Okay? This is latent class. Now, this is not correct. This is just a latent class model. I'm going to take the mixture model that starts with latent class, because we have binary items. The mixture model of binary items is called latent class. But then we're going to turn it into what this should be for the likelihood. Okay? Sound good? Okay, so the latent class model, anybody remember that? The probability that the vector u is equal to some response profile was equal to the sum, from class equals 1 to the number of classes of the probability of person at large is from class C, that's A, B, C, call that, times the product from U equals 1 up to the number of items of the probability for, actually, call this I, right there. The probability, item I for class C is, as answered as a 1, raised to the response to that person. I guess this is the case is U, person for the item, times 1 minus the probability item I class C, times 1 raised to 1 minus U person item. Does that make sense? I feel like I'm mumbling. Does this look right? The U is sort of throwing things up. Remember, U is our observed variable because I called it that in M plus syntax. But let's think about it, right? This term right here is your Bernoulli PMF, probability mass function, right? This is your class-specific item difficulty. This is a 0 or 1 binary response, right? So that should do it. We take the product across all the items. We're assuming independence of items, local independence conditional on class. Right? So this is incorrect. Why? Why will this not work for our DD? Let me ask that question. Right. I'll put it a different way. This is a marginal function right here. Right? This is marginal. So what we've done with this is we've marginalized across classes. But we have not marginalized across the data. Right? So for us, there's multiple ways. I didn't say you had to put a marginal model. Let's start with the simple model. Simple. There's nothing simple, right? None of it's simple. Let's start by just taking the closest approximation to this. And in fact, I hope you don't mind if I do some erasing real quick. This would be easier than my stupid handwriting. How's that sound? So I need that. Okay? No, stop it. This go away. All right. Want to see how to change it? Here we go. No! Come on, Templin, get your game going here. Like that. We're going to put the subscript P here just to remember person. Okay? So now, if we condition this on theta, right? It's not completely marginal. We can't use this in a likelihood function where we want a marginal maximum likelihood. Like if we're trying to optimize this with an EM algorithm or something, we really could do that. It's getting closer. If we call this thing up here pi, IC, and I'm going to call it person, right there. So if I call this person. And why does the person show up here? That's because the person has something to say about that probability. Not every person in an IRT model has the same probability within a class because each person is going to vary by theta. Right? But that's how you combine the two first. Now, if you wanted to make this the marginal model you could use for maximum likelihood estimation. Anybody want to guess as to what you do with this function? If you wanted to make it probability of UP. I'm hampered by my writing. I'm sorry. Can we just admit I'm just imperfect, okay? Can I just call myself imperfect? I'm trying, but my handwriting is terrible. I'm imperfect in any dimensions. Ask my children. My colleagues. Well, forget it. Don't even ask. CV of imperfection. But how would you get from here, right here, to that? With marginalized. Now, we've talked about this sum as a marginalization. It's appropriate to marginalize across what type of variable do we use? For which type of variable we use the sum to marginalize? Discrete. That's good. So why had to use a sum here? Because we have discrete classes, and we want to get rid of each person's class. Theta is not discrete. So what we have to do instead is integrate. Like that. Like that. So we have to integrate across the space of theta. And I just took this function and put it right there. That is our marginalization if we want to. Now, I didn't repeat my notation because my handwriting is bad, but that's how I would build it. If I wanted to go and estimate this, now, of course, estimating this we can't actually do, except for very small cases. The exact analytic approach, we have to then take this integral and then make it into a series of approximation, which becomes discrete, right? It becomes a sum again. Any of that I would have accepted. I'm not going to go and be nitpicky, just to start thinking about notation. But that's how I would look at this. Any questions about that? What do you think? I hear silence. Everybody bored of this? It's okay. It's like November 29th. I was putting my email this morning. It's like the last 2 weeks of fall semester got worse. I don't know about you. It's not bad for me. I'm good, but I'm concerned about you. Is it the worst for you? The last 2 weeks stuff? I don't know. And plus, it's like I don't know about you. I don't want to come back after Thanksgiving. If we could just start this semester 2 weeks earlier, I'd take that deal. End of Thanksgiving. I guess it was 3 weeks earlier. But what am I doing? Anything? Does this make sense? Do you care? It's okay to not care. Will you ever use this? Who knows? No? That's it. That's exactly right. And that's exactly my experience in grad school too. I'm never going to use this. 6 months later, I really wish I would have paid more attention. So what I'm going to give you here is some basics, right? I don't know that you need the notation as well, but if you read through mixture model notation, that's important. The other part I want to talk about is in general, I tried to teach this class in a way that we focused a bit more on estimation. And the reason for that, as you remember, was that we had like 15 different ways of estimating multidimensional models, right? We've got full information, limited information, Bayesian, and we've got some combinations in there that can work a little bit weird too, right? So, This shows up a lot. The bigger picture is why are we marginalizing it all? Does anybody remember that from estimation? Why can't we just treat all our person's thetas, all our person's classes, and all of our item parameters as just unknown variables and try to estimate them all? Pardon me?
The number of equations will be less than the number of variables?
Yeah, basically. Think of it this way. Slightly. Every time we have a person, each person carries some baggage with them. Call it that, right? Baggage. Every time we add a person, we keep adding parameters. And if we didn't have a latent variable model, this was just a simple linear regression or a logistic regression. Every time we have a person, if I'm just predicting x with y, or y with x, and I have a slope and an intercept, there's 2 parameters, no matter whether I have 10 people or I have 1,000, right? Always 2. That's what we want from an asymptotic point of view in statistics. That's the great situation, because every time n goes up, n is approaching infinity, but our parameters are constant, right? So for us, every time we add a person, we get 2 more parameters, right? Whether or not we have 1,000 people, 2,000 people, whatever, every person has 2 parameters we have to estimate. So asymptotically, n may be going to infinity with people, but the number of parameters is also going to infinity. And that is bad. Put it briefly. Because statistically, we need to have n go to infinity faster than our parameters to have what we call asymptotic consistency. Right? There's a paper that I would refer to in class, but I don't expect you to read it. It's an interesting read. But Neyman and Scott in 1948, they talked about this problem in economics. We have that problem in psychometrics. But look what happens. When we get to this marginal equation, that's where good things happen. Because now, in the marginal likelihood, we don't have a first theta. We don't have a first C. When you optimize this, when you use this likelihood function right here, if you're using quasi-Newton methods, if you're using Fisher scoring, if you're using some other full information maximum likelihood, you never estimate a person's theta. You never estimate a person's class. You may have two sums. You have to figure out quadrature points for theta, and you have to figure out what levels for class are. But those are just plugged in, and the likelihood is calculated that those two are there hypothetically. But it's part of a sum. Right. So basically, we're trying out each of the different versions. You know, I'm wrong on this too. No, actually, I'm not. I think I'm good. Oh, wait, nope. I screwed this up too. I forgot something. I need the distribution of theta in here. Right. This right here is our distribution of class. Right there. That's what we need. And this distribution of theta, if we go back to M plus the M plus syntax, right here. What do we know about it? It's normally distributed, a mean of 0, and a variance that varies by class. That's how I would refer here, because we have F here and F there with a semicolon. That means estimate the variance of that class 1, and then estimated class 2. So I forgot that part. So I screwed it up too. Okay. Yes. Yeah. No. Yes. I'm sorry. Thanks for letting me know. That look okay? Yes. Question. This right here. That is when we have an integral. That's the variable we're integrating over. It's with respect to. That's right. And an integral opens with this and closes with that. This is sort of tells you the range of the integral, and this says which variable will take that range over. Yes, that's a good question. Those of you who are more mathematically gifted, what is the name of this? I think it's the dimension, right? It's dy dx. It's like when we learn it like from a derivative perspective. But what is that called? I don't remember. This part is the integrand, right? The part in the middle. That's what I would say. With respect to, but it's d for whatever reason. And actually, in this case, because there's more than one variable, it's not even a d. It's like the script d, which really refers to like partial with respect to theta. That's that differential, like a differential notation. I think they call it differential equation, which we talked about. Right?
It's for partial.
For partial derivative. Yeah. This symbol here with this. The d that sort of looks more script-like, that's a partial. Like we take a partial derivative. If we have a nonlinear function of x and y, pardon me. Let's say two things, theta 1 and theta 2, and we want the derivative of that function with respect to theta 1. That's called a partial derivative because there's this other variable floating around. That's a good question. Glad you asked that. Yeah, what we're doing here is basically saying, in this equation, there's a variable named theta. We want to basically integrate over it only, is what it's saying. Yep, you're welcome. Interestingly, the notation for the class is a little bit weird here too, right? Because technically speaking, we're estimating theta and class simultaneously. So what we really want is a distribution of theta and class. But here, we have a set of class-specific parameters and a set of theta variances conditional on class. What we're end up doing with this is breaking this into the following. We're estimating the distribution of theta conditional on class times the distribution of class itself. Now think about that. Why I'm posing this to you, because if you're ever in the mixture model world, there's a ton of alternate parameterizations that are equipped, right? I don't know what this joint distribution actually looks like. It's some mixture distribution because theta is continuous and the class is discrete. So it's some weird mixture. But to get it is a proper distribution, we condition on theta and multiply by the marginal of the class itself. And that's actually what's happening here. We go a step further, right? This thing is that normal distribution. And this distribution of class is actually described by that parameter A to C. Because remember, class is multinomial in this case. So the A to C is sum to 1. Is that too much notation for you? This is absolutely multidimensional, by the way. We've got a theta dimension, we've got a class dimension. So, what do you think of mixture IRT models now that you've done a homework on them? I know, the homework was before break. How long did that analysis take to run for a lot of your homework? Too long? Yeah. Especially when you get to like 3, 4, 5 classes. Like two classes, you're like, yeah, that's a little bit longer than I expected, but you know. Yeah? But you did it. Most of you found the mixture IRT model fit better. Go figure, it's going to. Right? That's like saying, think of what the model is for one class model, right? In one class, the IRT model says every person gets a different theta. The one class, not IRT, late class model is, doesn't matter where you are, the only thing that matters is item marginal item difficulty. So yeah, marginal models are absolutely, theta is much more complex. So I expected that to be the case. But I thought I saw for some of the analyses, there were some cases where, at least with late class analysis, you get close to the same model, like AIC and BIC, eventually, but still not in the same ballpark. It's still not that close. I mean, starts close, but not super close. But that always happens. Because, think of it this way. Actually, let's go back a little bit more. I'm just totally freelancing today. I hope this is okay. But, think of it this way. If you take, let's imagine you have a simple linear regression. Way back in like first stat class, right? Y is your outcome, X is your predictor. X is continuous, right? You estimate the model, you get a residual variance of X. Now, go and take X, divide it into 2. Group 1, group 2, with an average X for each. Do the same model. Which model describes more variance? See what I'm saying? Right? So if we did this, Y, X, we have a bunch of dots around the line here, right? That's that. And we have some sigma squared error here, right? Now, compare that with the following. Let's cut X in half. Figure out the mean X over here, the mean Y over here. Let's make that model. That model, yes, has much less variance explained. Because you've taken all the possible values of X and shoved them into one number to represent them. So they're not covariant with Y as much as they will. No, there's a group effect, that's it. Right? In basic statistics, this idea of splitting the data, if you look in, I don't know, 15 years ago I was in the psych department and the social psychologists were doing this all over. They call it median split. They take a split of X, and they wanted to do that so they could run an analysis of variance, and everybody's like, whoa, hold on, that doesn't make sense. We seldom want to discretize the continuous variable. I say seldom because there are times where we actually might want to if we want to look for non-linear trends. Looking at trends and means might be easier. But that's effectively what's happening in this comparison of theta in class. Right? Theta is continuous. Class is discrete. Within a class, people are treated equally. Whereas theta, there's heterogeneity in the whole place. So we would expect an IRT model to always fit better than its version of that model where there's no continuous latent variable. Almost always. Weird. Huh? Cool? Weird? Cool. I don't know. Forever. All right. Any other questions? What do you think of this discussion? Is it okay? Tying back to homework. All right. So, any other questions on homework before we move on? Yes, Mubarak. About printing the... I'm sorry, the what? Interpreting what those are. Yeah, that's hard. Great question. I have no idea. In the latent class model, I look at the item, those probabilities, and I think, if I'm not mistaken, almost every, you might have had a plot of those probabilities. And I think that's where I would look for the latent class model. For the mixture IRT model, I'm less clear. Some people that I've worked with, they usually fit mixture Roche models, in which case there's only the B parameter for each class. And they've looked at the B parameter almost the same way they looked at the class probabilities. Like these items are more difficult for this class versus this other class, or they may flip. If you remember that plot of the mean, sometimes you'll see class 1, class 1, class 1 type of thing. And they would interpret that as like saying, well, class 2 has an easier time with these items than class 1 has an easier time with those. That's about all they could go. And then from there, they might make some speculation as to what that means. If the items you think are easier are all on the same like academic standard, maybe these are class 2 are people who know that standard better, or something along those lines. That's the closest I can get to it. But that's about it. Does that help answer? Thank you for asking. Yes.
We look at the M+, out this class means. This is any indication about the class.
You could if you look at like the, but yes and no. Because, let me go back to this real quick. Here's where it gets to be really weird. Right? If this model fits well, right here, that means each class, with the exception of the very first loading, we're basically saying that each class could have significantly different measurement model parameters. And the question then becomes, is theta the same then in each? I don't know if the psychometrics can really describe that. Right? But I will tell you that, theta will have a different mean and variance. I mean, you talked about the, maybe this is what you were saying. If we look at the variance of theta in each class, that might be one clue. This class is more homogeneous, this class is less homogeneous in terms of their ability. But then within that, understanding anything else about means may be harder. I guess you could go back to the original data and try to come up with the weighted average of like the item responses, like or to see what that might be per class. But then getting to that might be hard because not only do you have to wait by like the class, you've got to worry about that latent variable too. But does that help a little bit? There have been other people. I've mentioned this. I think I mentioned this in class a few weeks ago when we were talking about mixtures. I knew people who would fit mixture models. If you think about it, this is like an invariance model. Like we're looking at diff. We're looking for different item parameters. This is it. We allow these parameters to be different with the exception of one, and we could even play with that a little bit. We could choose a different marker item in a different class if we wanted to, right? And so there have been papers written and people who've done where they basically said, can we use mixture models to detect different items? Because literally, the parameters are different throughout these classes. We just don't know what the groups are. And then with those groups, we could try and predict whether or not what's most influential about a person being in the group. We could go and take, for instance, if sex, a person's sex was thought to be, like typical diff analysis, we look at diff of men versus women, for instance. Well, we might want to predict group membership in this model by sex, a person's sex, and to see if that separates the classes as well too. So that's where people will add more. That goes down a different problem methodologically because now the groups really don't exist, and these models are really sensitive to model specification. For instance, I think I told you this story, but I'll tell it again. When I was working at Georgia, one of my heroes in the field, Al Cohen, I was working with, was great. Loved mixture Rosh models. He said he liked them so much because he felt like in the different groups that represented different strategies people were taking for items. Like for this strategy is easier, this, and it made very good sense. But at the same time, I was studying mixture models just because diagnostic models are types of mixture models. And I was reading work from Dan Bauer and others early in the early 2000s and talking about sensitivity of mixture models to model specification. So meaning model misfit. If you misfit, if it doesn't really fit a unidimensional IRT model, the mixture model's only way of fixing that is to extract more classes. So they have these things called spurious classes. Why that matters is if you're trying to understand what a class means and that class shouldn't be there, you're going to do two things. You're going to make speculation about people that probably isn't true. It's only just an artifact of statistical noise. And the second thing is psychologically, once you make that decision, it's really hard to move on from it. Right? And then just decision-making literature, we call it anchoring. Right? We're going to anchor our expectations on this. If you want to see anchoring, give someone an exploratory fracture analysis. Tell me what these factors mean. We've just anchored people for years, right? Anyway, those are bad. But in that sense, I did a study with a postdoc where we simulated 30 item assessment. Right? 29 of the items were Rosh model. Right? Had the same equal discrimination parameters. One item, unequal discrimination. Right? We estimated, we only generated one class of data. We fit a mixture Rosh model. Remember, mixture Rosh model. The only difference is 30 of the items have different classes, different difficulties, right? Turns out that mixture Rosh model in the simulation more times than not wanted 2 or 3 classes. We didn't generate classes. We generated 2 PL where one PL data with one item being 2 PL. We fit this model 3 classes, 2 classes, 3 classes, 2 classes coming out. So what I'm telling you with that is, when you start to interpret class, leave space in your brain to not anchor completely, because it may be an artifact of analysis. And that's the danger with mixture models. The danger of class analysis in general is if they're fully exploratory, they are subject to wild artifacts that may not actually be true, but they are true because if you think about how we choose which models best fitting, it's always based on AIC or BIC. And that's just telling us, how close this gets to looking like our data. Well, the only way this model will look like our data is to add more items. There's no other fix to it. No, I'm sorry, add more classes. Yes.
Is that item had additional information for it,
Yeah, kind of like that. Yeah, basically it did fit the assumption. So if you think about within a class, all the difficulties are equal, all the discriminations are equal. Right? So when it goes to that item, that discrimination shouldn't be equal to the others. And so it made a class of items where that was closer to that group's class, right, for it. But basically it was approximate. The other thing at the end of the paper we did was we flipped this on our head. We basically said, here, if I scroll up, this model right here is the probability of we've integrated across class here, right? What we ended up doing was calculating this by integrating across class and coming up with an ICC. What the ICC for that last item started to look like once you added more and more classes is it went from not looking like anything like with one class, it's a Rosh model, it's not going to look the same. 2 classes, 3 classes, 4 classes starts to almost bend itself and look exactly like it. Where the mixture model is approximating it through a set of discrete approximations. So, glad you asked that. That's a question. Would you like me to go down the next rabbit hole of models? Flash forward to like 2017, I have a working at KU and I have the benefit of working with a great student, Lu Chin is her name. She's in somewhere in Maryland. I think she works in Howard or something, or House or something. Anyway, she wanted to do something called semi-parametric structural equation modeling. Ever heard of that before? Semi-parametric anything? First of all, semi versus non-parametric, those words are sort of meaningless. But what they were referring to there in a semi-parametric model is like fitting an infinite number of classes, but you can't do infinite computers. So they just pick a large number of them and aggregate or marginalize across them. So they're fitting structural equation models in each class, but they don't care about the class. They throw that away, they aggregate across and marginalize across the result. Try to get different trends in data. So for instance, if I was only locked in on, if I only knew the Roche model, which thankfully I don't, if I only knew that, this approach, where I have lots of classes, will yield an ICC that's not Roche. And that is important. So they take it to an extreme. The semi-parametric SCM type models take this idea of classes to an extreme. They're fitting like 40 or 50 classes. Now DCMs, we fit like thousands of classes also. But the point is not the classes. In fact, we don't even recognize class information. We throw that away and we look at what the aggregate result will be when we marginalize the process. And that doesn't look like a single SCM, it looks somewhere in between. So that's it. Yeah, so mixture models. How many of you like them? You're worried to say it. I love mixtures. They sound really awesome, right? And actually, it was like I was in grad school. I didn't take a class on this either. Thankfully, I had research to do on it. And I get out of grad school and I'm looking at this flurry of people writing papers like M plus introduced mixtures to M plus in like I don't know, circa 2000, 2001. There were people who added stuff for growth mixtures at SAS, like there's proc traj for trajectory, for growth mixtures and stuff. People are like, yes, these are so awesome. We can find groups in our data. This is great. And by like 2010, everybody's like, yeah, this is a little overdone. Not quite. They're good if they're good tools. They're good for engineering. They solve some problems that other places can't. But if you're using them and trying to really believe their results, that's dangerous. I think it takes a lot of validation. Even then, I'm skeptical. You're going to claim this class that you just are trying to describe basic characteristics of the model is unique to this other class. How are we going to find that? I don't know. So that's all. And by the way, if we go back to the idea of multiple strategies on a test, my argument would be that you can't necessarily find that psychometrically. You have to set up an experimental design to elicit them in a way. Either that's changing the item or changing the structure of the item or otherwise. The interplay between psychometrics, tests, and experimental design, even though our program calls it educational measurement statistics, I feel like we're often siloed into places. Always remember design. It's the thing that matters the most. Our design, what we're doing is an experiment of sorts when we deliver items. It's just a weird version. Don't forget it. Anyway, down the rabbit hole. Lots of rabbit holes today. Lots of tangents, but no, tying things together. Hope that helps a little bit. All right. Anybody bored? Any other questions on mixtures? Ready to close the book except for the DCM homework. Close the book on mixtures class. I'm always willing to talk mixtures. So after class, if you have questions, find me. Or next semester, if you can think about it, find me. We're good. Okay. All right. So today, I'm deviating from what I thought about doing for a lecture. Mainly because when I looked at what I wanted to do for my last lecture, the content of my last lecture, I wanted to actually say some things about scores I don't think you get in other places. And the lecture here, by the way, this is a sit back and relax type of lecture. All right? Just talk through. I've got some example code. I'm not even going to do it in SAS. I'm just there to tell you what I'm saying, to give you the evidence that what I'm saying is not made up. But I'm going to talk about what's in the score. And I want to do that first here, because it applies in unidimensional settings. In fact, all of today's unidimensional scores, even though we're in a multidimensional class, unidimensional scores. But it's important in understanding the modeling framework that we're going to get to next week for multidimensional scores. In fact, let me start with the question I'm going to ask you next week. You've been analyzing these data this semester that have multiple standards. Right? And multiple subjects. You have ELA, you got math, you have multiple standards within each. Let's just take one subject. Let's just take math for the moment. Okay? If you're in an assessment program, do you, and somebody says to you, I want two things. I need a score for each standard, and then the overall math score. How do you do it? What's that? You could, but so the Q matrix, and you put it in a multidimensional model. So this is, by the way, this is a test final here. You're passing. Don't worry. We're gonna get there. Everybody's gonna pass. Don't worry about that. But let's walk through. This is the scenario, right? I'm in a large-scale assessment program. I'm your state assessment. I'm going to give out your state assessment score, but my districts are killing me because they need something about each standards. And Lexi says, you want to put it in a Q matrix. So each standard is a column in the Q matrix. So we go and get 4 theta. Let's imagine we have 4 math standards. A, B, C, and D. 3.NA, takes a lot, right? A, B, C, and D, right? So we have a score for A, a score for B, a score for C, a score for D. You're cool with that. Great. That satisfies the standards. What about the overall score? Oh, there you go. Okay. Glad I'm not going to tell you the answer yet. So we're going to talk about next week. And we're going to talk about scores today. But this is why this comes up. Because each of those things you just say actually implies a psychometric model. Did you know that? What is it? We're going to talk about that. That's where it comes up. Let me tell you what I think happens now. At least it happened in the place I used to work, Kansas. The state made a contract with my employer, University of Kansas, and said, you're going to deliver our state tests, and you're going to give everybody a math score. ELA, stuff. Let's just take that, right? Now, here's your math score. But would you please give us something about each of the standards or the domains, right? Algebra or numbers, base 10 or something like that, right? And so you said, sure, we're going to use the 3PL. We'll come up with a scaled score for your math scores. And we put it on a scale between 220 and 380. Very familiar with this data. There's your math score. And then what we're going to do for each of the, let's just say domains, right, in each grade, we'll give you a subscore. That subscore will either calculate by adding other items together, or just taking the item parameters from the items that were part of that. So take all the items that measured, let's say, numbers in base 10, NBT, which is the domain in early math, elementary math. Take the item parameters from that, and just make your theta with those item parameters. See what I'm saying? Right? So your item parameters came from the full model, the 2TL, we're going to create a subscore with just those item parameters. You hear what I'm saying? You see the difference? Right? The overall math score were all the items. With 1 2TL or 3PL, here's your theta, rescaled. Right? The other idea for the subscore was, let's say I have 60 items, take the 20 that were numbers in base 10, take those A, B, and C parameters, and give you a theta for those. Right. And the alternative to that might be, forget that, just take the results, say there's 20 items, and give you the sum of the 20 items. Right? How we doing? Frowning. You understand it? What do you think about that approach?
Seems like multi-dimensional.
Could be. They're all unidimensional, yes. But what do you think might be a problem with that approach? By the way, we're going to come to this next week too. So you're getting close. That's right. Let's talk about that for just a second. The items that reflect the construct, right? So if let's imagine a 60 item test, and all 60 of those go into the 3PL and give you the math construct. And then you take the first 20 that were numbers in base 10, and those go into numbers in base 10 for the theta. But the item parameters come from the overall one. The items in the model doesn't care then. What I would argue is that 20 reflects a shorter test. right? Instead of all 60 items as this person, we have 20. Right? What if we did 21? Okay, it's closer. What if we made it so that the test was 50 items of numbers in base 10 out of the 60? Well, you imagine those betas will look like. Very almost very similar, right? And so what I would argue with you, if you do it that way, you're, I don't know if I'm arguing, I'm just going to throw it out there. It's very clear to me, you've just created subscores where the only difference is the number of items that's assessed, but the constructs are identical, and they're not a subscore. Once you put in that 3PL on the overall map, you do anything else with it, you're doing overall math, because it's calibrated on overall math, whether it's numbers in base 10 or otherwise. And that short test will converge to the same theta as the number of items grows. I'm going to show that next. I had a consulting appointment over an argument about this one thing with some people from the Center for Assessment of all places. Anyway, they were wrong. I'm going to show you. And that's why I'm making an election. I'm not petty. But it does describe an issue in the field. We start making subscores, and we think every time we make a score, we think it reflects the construct, as you would say, right? But it only reflects the construct if we put it in a model where it was measured with the construct by itself. Now, what about the case where if we just added those 20 items together? If we disregard the IRT parameters, what about that? Well, what's the model? I don't know. Wait till this lecture. The other part of that is that might be valid. The bigger problem is if that model holds, if that sum of items holds, and you have unique, distinct subscores, then your overall math score is invalid because you have a multidimensional assessment and you can't give unidimensional scores. Right? So the flip is not good. So the bigger picture is how do we do both with one modeling approach? Because the methods that you see now, when you give one score and you give subscores, don't do that in practice. In theory we could, but in practice we can't. And this is why I'm trying to teach you all about models and modeling. It's my version of methodology. Because to do educational measurement, well, you have to be a methodologist. And seldom is that top. You look at the standards, the NCME is making like core competency stuff. Really, what you just say is learn methodology. You're going to be using it all the time. I don't think that happens a lot, or as much as I'd like to. Yeah.
So I'm thinking of key metrics. If we add like one more domain and added one to all lines.
Yes.
That would be all lines.
You're foreshadowing a bit next week.
Okay.
That would be called a bifactor model. We have a general factor that loads onto every item, is measured by every item. And we have specific factors, perhaps being the standards. I would say you're closer, but not quite there, because it turns out to identify that model, you have to allow that general factor to be uncorrelated with the specific factors. And if you think about each item response, and I'll have more on this next week, so just listen now, there'll be more detail mathematically next week. What you're doing on each item, if you think of an item response, if you look at this part right here, in this part right here, it's hard to see. Here, let's build it. Let's make it an intercept. Beta 1, theta 1 plus beta 2, theta 2. Like that. Right? If this were a linear predictor in a linear regression, we call this a multiple regression. And we're saying, this is the impact of theta 2. Maybe this is our general factor, and this is our specific factor right here. This is our impact of our general factor on the item. But what do we always say about that when we have a multiple regression? Controlling for the presence of theta 1, right? What that means from a measurement point of view is that everything that's in the general factor in this model is everything but the specific factors. So now your math score reflects math except for the standards. That's a problem too, right? It's going to be highly related, most likely, even though you fix the correlation to be 0. In the posterior, it will be related, most likely. But this now becomes almost like your leftover term. That's the stuff I can't fully describe after I describe my stances. But there's another similar approach. But thinking about it, they're actually intertwined psychometric history. This is very related to a different type of model. The higher order model. I'll just say higher order. We'll talk about those next week. All right? But that's how I view it. Believe it or not, I remember when I worked at KU, I had a colleague who worked with a vendor, shall we say, well-known vendor of interim assessments, and they were very proud that they were going to offer this as their scores. We're going to give you map and standard domains. And they had this great poster, and they had like, and it was this model. And I'm like, yeah, that's math without those domains. Oh, that's bad. Right? Model fit is great on that, by the way. This model, the five-factor model fits everything because that general factor becomes like everything else. Right? It's not in the model. But great thought though. All right. Other thoughts. So I'm hoping to set the stage. That's why. So I was going to talk about that. But I'm like, wait. Before I talk about that, I need to talk about this. Some of this you may have heard. There are slides in here I know I gave in Bayesian. For those of you who were in Bayesian before. Mimics. But yes. We'll go through this. Okay? We'll talk about scores. Any other question before I jump in? I know, I've already wasted half the class. By the way, I'm not getting through all this lecture. 112 slides, right? I went a little crazy before, so I'll go quick. These are from I gave this, so long story short. You know the class SEM that Lisa teaches? Right? Would you believe that she and I combined forces on that class a while ago when I was at KU? These slides were before I got to combining forces. The last time I taught SEM by myself had this involved. Because I was teaching at Ed Measurement program, or a lot of students went to Ed Measurement. So this is my talk about it. So we're talking a little bit about some scores, what's in them, relating some scores to factor scores, and maybe a little bit about reliability in this lecture. This is a sit back and relax. There's nothing on the test for this. Well, final is the final, but we just experienced that. What I just talked you through is what the final will sound like, right? Oh, that's great. Have you thought about this? Have you thought about that? Just kind of walk through. Okay? All right. And I may cut out the last part, which is, hey, if you have scores and you want to use them for something else, what do you do? Because that's not easy either. I mean, you just take your score and just plug it in a regression or a linear model. Yeah, that's right. So most people do, right? Not quite. Scores have error. When you do that, you get about the error. It's actually prompting me to think about teaching that missing data class. It's coming. I know many of you are done with classes after this. But I may feel the urge to teach it in fall, though. We'll see. Because of that. Other things too. But. All right. The big picture is this. That last point. If you latent multivariate analysis. What does that mean? Multivariate models with latent variables. The bigger thing is I mentioned. Okay. Let me set it up in a context maybe more familiar. We require a GRE to get into our program. I say that like that because there's some debate amongst faculty about the value of it. Right? Every one of you took GRE. Right? Unless you enrolled in a different program and transferred into our program, which that's okay. But leaving that aside, we require the GRE. Do you realize the GRE puts out a book called The Guide to Use Test Scores using the GRE, right? Have you seen this book before? Let's see if I can. But I just bring it out to you. Caps lock. I'm just going to yell at it. Guide to test scores. Using GRE scores is called now. It's an understanding one too. This is like their. There it is. Guide to Use Scores, PDF. This is like a technical manual, but not entirely exactly the same. One thing I wanted to note on this, in recent years, validity has been boiled down to a few paragraphs, and they don't actually report any validity of the in the guide. if you go dig a little deeper, you can go to their website. They give you a set of papers where people publish about GRE. That's it. So let's think about validity of the GRE. One of the standards for validity of the GRE was to take the GRE score and predict your first year GPA in grad school. Right? So if you're ever in that situation where you want to do that, that tells you sort of how much is the GRE predict how well you do. Now we know the GRE scores are truncated, and not everybody goes to grad school who takes the GRE, so there's some design considerations we have to worry about, some sort of attenuation we may have to worry about. Well, let's talk about that prediction. It seems fairly straightforward. Here's your GRE score. Here's your value of your GPA. One predicts the other. Right? No problem. Except each person's GRE score has a different amount of error. Let me see if I can find it. Do they have the conditional standard error of measurement anymore? They used to have conditional standard errors of measurement. They take those out. Oh my God. Anyway. Okay, I can't find it. Anyway, long story short. Swear to God, I got it. Anyway. Okay. Long story short, GRE score has measurement error to it, right? So doing that prediction is going to be fraught with two problems. Number one, the regression slope is suppressed. It's suppressed because of what we call attenuated data, right? The lack of reliability and the lack of people who are on the lower end of the GRE getting into grad school are going to make that number biased, and it's biased negative. So it looks smaller than it really is. But second, if you just use the score and you disregard the measurement error, the conditional standard error of measurement goes with it, the standard error for that score shrinks also. And now the question becomes which shrinks faster. Because if you remember, that slope, if you're trying to establish the GRE significantly predicts your first year GPA, even if it's a mild effect or a moderate effect, small effect size. That slope, that ratio of slope to standard error is your Wald test for it. That's your significance test. Or one of. You can do a likelihood ratio, model comparison, you can do a score test. There's different ways, but just take it that way. That's how we normally do it. So the question I have is, what goes smaller or faster? Right? Does the lack of reliability shrink the slope faster, or does it shrink the standard error faster? In my experience, the latter, actually. Standard error is better. So what happens to the Wald test is it looks even more significant, if there is such a significance versus not. But the problem with that is, where I'm getting back to on the slides, is that the error will propagate. If we sort of forget measurement error when we do analysis in scores, anything we use that score for later on, that error still is there, we just don't know about it. And that brings about an overconfidence for those analyses. It also brings about a bias for the analyses. That's worrisome to me as an analyst. And about you, that's it. So how many of you have ever used a test score in a secondary analysis? Raise your hand. I mean, literally, it's like test score users anonymous here, right? Yeah, my name is Jonathan, and I've forgotten error in analysis for a test score, right? That's what happens, right? I'm not here to judge you. I'm here to talk about the methodological issues with it, because we should be aware. So that's one of the motivating factors to this lecture. The second motivating factor is, when we make a score, what assumptions are we making from a model? Make a sum. If we were just to take a sum of items, what are our model? Is there a model there? Do we have an assumption for it? Doesn't sound like it. But I'm going to show you there is. What if I told you there is? Not only is there not a model, it's easily testable, and we should be doing it, but we're not. Those of you in theory and technique right now, we don't have that as part of your class. But that's I'm attacking theory and technique now. The whole thing is BS. It's not. The purpose of theory and technique to me is more how you apply mathematical statistics in the context of tests than it is the actual results you're finding. Because those results are kind of old. But all right. Now, there are many cases where you can't do a simultaneous analysis. Look, the whole purpose of the term structural equation model is to do a simultaneous analysis. Right? You may have seen it, right? If we have let's say theta right here, we have a set of a measurement model, and we have three indicators or three observed variables, y1, y2, y3, and we may want to predict this with some other outcome x. This is the way to do it, a simultaneous model. Because now in the model, the measurement error has a place for it. Right? It's contained in the model itself. That's the whole purpose of why structural equation modeling is a field. Right? Because in this scenario, we have a latent variable we want to do other things with, maybe a path analysis with, maybe much more complicated. Measurement error screws this up. We need something else with it. Right? We need to figure it out. But we need SEM for this. But oftentimes we can't do SEM to do simultaneous analysis. Right? For instance, if I go to our college and I say, I want to do a validity study on the GRE, I may get lucky and they may give me a bunch of GRE scores and a bunch of GPAs. But none of the GRE scores will have measurement error, and the GRE scores don't have their items. We don't have item level data on people. Right? So the first thing, if you get out of this program and you're ever in the shoes of working in research with people and they're doing assessments, have them keep their item level data. A lot of times they throw that away. Isn't that right? With Woodcock Johnson. Yeah. They just once they give you the score, everything else doesn't matter. The score. Right? That's right. And then they send you threatening emails rather than start. In this lecture, I will talk about a threatening email also, not to me, but to some other background. I may get a threatening email on this one. I'm not insinuating that GRE is bad in this lecture. I was using it as an example to set the framework. This is a very common practice. So, oftentimes we can't do simultaneous analysis. So there are methods that we could do for it. That's where missing data is important, by the way. Missing data classes are important. Understanding the concepts of missing data are important. That's why I'm not teaching. But let's talk about what's in the sum score. So this is really interesting because as a student, as a teacher, as a faculty member, I found some scores to be really contradictory how they talk about them. First of all, what's the sum score? It's the raw sum of your item responses. If it's binary data, it's just the number of correct responses. If it's liquid data, it's the integer you gave every item. Sum them all up. That's your score. I've heard people say, some scores are almost always okay. Those of you who went to this is, I've heard that argument there. Some factor scores are okay if they come from some strange sounding model, like I'm going to use the GRE. Well, I know the GRE uses an IRT model, so therefore I can use the data for that, right? Or there's otherwise factor scores are the work of the devil, or another way of putting it, factor scores are so bad we should never touch them because there's this thing called rotational indeterminacy or factor indeterminacy, and we can never trust them. In fact, I've had my first job at Kansas, someone say this, and then we went into a meeting where we used these. It was like, you realize that's a factor score, right? Yeah, but it doesn't look like one. Anyway, so let's talk about it. So the question I hear is, why use structural equation modeling or CFA or IRT when we can just use the sum of the items, right? Sometimes Lisa calls this the add stuff model. Some scores can be used to do almost everything you've used it. And the current practice in educational research, I would say, this is not me in the testing industry. This is me working with other faculty on studies where we have measures of some sort. Seems to be, let's use the sum score until a reviewer says we can't. And at that point, probably need to do a factor model to show the fact that the dimensionality is correct, but then we go back and use some score again. And you all found out in this class how factor models work for finding dimensionality, right? Highly variable. So that's what that happens. But let's talk a little bit about this. To show this concept, I grabbed some data. I have this, I think Lisa uses data in her SEM class. I help collect these data. These are gambling data from 2001 in a casino in Peoria, Illinois. Yeah, living close to there now. There are three liquor type items about gambling. It doesn't matter what the point is right now. Just I'm going to use them to sum up. I also grabbed three binary items that were reading items from my data that you're using in class. The difference being one being liquor type items, where a CFA gets used more often. One being binary items, where you shouldn't use CFA for, right? Okay, that's the setup. There's the sums, the sum of the liquid items. Now, these are items asking people how much they want to gamble. And they're sort of, some of them can be extreme, like I've stolen money to finance my gambling. Well, we're collecting data from a casino boat. Actually, this frequency, this is a mix of different samples, one of which would have no access to gambling whatsoever. We would expect the score distribution to look like this. Most people at this time in 2001 either had limited access to gambling, so therefore had no problem with it, or just didn't have a problem with gambling. Gambled responsibly or didn't gamble at all, right? Very few people have admitted to stealing to finance gambling. Let's put it that way. And here are our three binary items as well. We have roughly equal numbers of people with one correct, two correct, and then a little bit fewer for having them all correct, and then there's a sizable number who answered none of them right. That's our data. Questions on data. Why I'm showing you two data sets. Remember, these are two approaches. It's modeling. Okay. So I'll do this slide and we'll take a break. Okay. So the use of the sum scores brings about a discussion about the psychometrics that underlie them. Typically, this falls under classical test theory. Some of you are in theory technique, but all these methods that we talked about there all works the same. But the big picture is the score is a sum of the items, right? But what we're going to do, what we're going to try to establish is classical test theory is a model. It's a restrictive model. And we can actually quantify its assumptions on each of the items. Have you heard of any assumptions in classical test theory when you're adding things up? Those of you in theory and technique, they've talked about assuming things. You need to assume to add up items. What are those assumptions? Anything. Okay, forms, yeah. Basically, they just, you have a test form, add them up, right? We're going to assume that the items all measure the same thing, that's one. Unit dimensionality, I'll go with that. Because otherwise you'd have multiple sums, right? After that, we have multiple forms. Well, we know that the forms may have different meanings and difficulties, and so it's where we have linking or equating, right? Am I missing anything? Uncorrelated, yes, that's also true. How about a step further? How about the relationship of each item with trait? I'm sorry? How equivalent? You may have heard that before, but actually I'm going to argue that's correct. It's actually more strict how equivalent. While equivalent means effectively each item measured has the same covariance with trait. What's that? Yes. Essentially, how equivalent each item is. Discrimination is the same. Yes. We'll go a step further. It's actually more than that. Yes. Yeah, that's what we're talking about. Basically, what we're going to do is I'm going to show you the classical test theory is a confirmatory factor model. And it's a really bad one, too. And we're going to go quantify tau equivalence. Now, those of you in Lisa's class probably can do this already. If I give you a factor analysis, tell me what a tau equivalent model is with it. Can you tell me what a parallel items model is? Or the other model, which is everything's estimated, sometimes we call that congeneric model. What's that? We'll get to that in a little bit. How about we take a break 10 minutes? Come back a little bit after 2, at least top of the hour. All right, stop recording. Okay, we're not getting through all the slides. You have all the material though. I put them all up. You can see them all. Those of you who like missing data. The end of it talks a little bit about missing data. We probably won't get that, but we'll see. All right. So basically what I'm trying to tell you is this. When you do classical test theory, I didn't realize this. Hong, you mentioned tau equivalent. I believe some scores were like tau equivalent models. I was wrong when I made this lecture back in 2015. They're actually more restrictive than that. Tau equivalent is the assumption that we use when we talk about Spearman, not Spearman, Cronbach's alpha. Right? So go a little further. All right. You know the classical test theory, there's a true score. In CFA and IRT, we often talk about factor scores, some latent variables of some sort. The key difference is, in classical test theory, you've seen this slide. This is from Lisa and I think she started this slide, but we both had similar versions way back when. The whole test is the unit of the analysis. It's a sum of right? Whereas classical test theory, IRT, is the item. So this is the classical test theory, quote-unquote, model that we often depict. If we could actually take a total score from somebody and make it into two parts, the true score and error. You've seen that? Everybody just loves that model. So the expected value, turns out, if we say that error has an expected value of 0 and then it's uncorrelated with true score, then we can say that the true score is what we expect y to be. If we have a long enough test, or if we administer a test multiple times and come up with an average, that will effectively converge to our true score, the test should, right? So this true score is why you created the sum score in the first place. Technically, this is the sum score here. But the sum score is your proxy for the true score, because your sum score is what you can observe. And in the long run, the true score and the sum score should converge, so therefore, right? Am I saying anything out of line with what you learned with classical test theory so far? That's good. I want to contradict that. So we haven't made any distribution assumptions. But even if your data fit a one-factor model, when using the sum score, the error portion is actually part of the total. Right? So there will be error, most likely in the total. How often is it that what you observe meets exactly the expectation, right? Where the error is exactly 0. So we know this. And so therefore, we come up with ways of bounding the sum score. There's all sorts of ways of coming up with a conditional standard error of measurement. Some of Felt's work came from this university while he was at this university, or some of the other methods that you may not aren't as elaborate, where it's unconditional standard error of measurement, right? Like something based on reliability of some sort. But because the classical test theory model does not include individual items in it, just total, the items have to be exchangeable, right? You can replace one with the other, no big deal, right? And if the model fits, then more items means better reliability, right? We've talked about that before as well, too. I don't know if I want to talk about this. We can talk about it. We'll talk about reliability a bit, too. The goal of classical, one goal, I wouldn't say, a goal, not the goal, but a goal. One goal of classical test theory is to provide a framework for which we can use a model to describe reliability, right? So here, we can come up with a decomposition based on the variance of that total score, right? All this is just describing the mathematical statistics. We went over that in class, what the variance means from a hypothetical perspective. In classical test theory, basically we say the variance total is really the variance of true plus error. We can split these two terms. Actually, we can say this is true score plus variance of true score plus variance of error plus 2 times the covariance. But because we assume that the covariance is 0 or error is correlated with true score, that goes away, and you're left with this. This, by the way, is like fundamental measurement. If we taught an undergrad class, this would be in the undergrad class, right? You've seen this. Everybody's nodding. Yes. So the variance total is variance of true score plus variance of error. And then we talk about reliability as a ratio of the variance of total or true score to the variance of total score, y, right? Or put another way, we substitute y with this variance of true score over variance of true score plus variance of error. Right? So what do we have? We have y, which is our variance of the observed subscore. We have the variance of true score. This is what we would observe in variation in our people. That we're not describing, that we're not explaining, excuse me. This is just what we call the individual difference, right? People vary in what they know or how they express what they know. So that shows up. And then there's the variance error, which we'll define as measurement error. Right? Somehow. Could be anything. Bad day for the test, bad for who knows what, right? Well, how do you define reliability? It's going to depend. I want to talk a little bit about, I guess this is a pile of things in lecture. We talked earlier this year, I mentioned parceling earlier this year. Yes, I know why. We talked about parceling when we came to the test manual for the Iowa test. The ICE test. It was in the validity section, so it's not what they do, it was in the validity section. Let's talk about parceling. Parceling is a sum score. It's like saying, I'm going to take the sum, let's imagine I have 5 items measuring math, 5 measuring reading, and I want really the correlation between the math score and the reading score. So I take the 5 items, take the sum, use that as a variable. Take the 5 reading items, take the sum, use that as a variable. I could put that into a simple SEM or just estimate a covariance between the two. That's what parcel is. So basically, parcel is sum of data, then analyze the sum. The parcel is the sum. It's like a lot of fields do this. We recreate terms to make them sound either unique to our field or like new and better. But when you hear parcel, what do you think? Not post office. You think not mail, sum. Add things up. I'll just say it. You mind if I do? I've been seeing this whole class. We've seen here. Add shit up. Right. Just gonna add that trash together. Add trash. Maybe that's more polite. The T. I get it. Hold. Okay. So when you do parcel, though, I want you to think about this when I'm talking about this class too. Okay. So what people will do. Remember, this even started when I was in SEM. It was ages ago. Taking Rod McDonald's SEM class, and one of the class projects with my friends took our gambling items, which had 10 dimensions, made parcels out of each, so made a sum score for each of the dimensions. Right, those sum scores were not overlapping, there were some for each dimensions, and then put those 10 sum scores into a factor analysis. Right? So that's a secondary analysis of data, effectively, right? But what I'm going to tell you here is technically, if you knew the model behind those, or you knew a model analogous was behind those parcels, you could do it all simultaneously and test model fit parcel too. Because I have this belief that parceling is done because if you know what you're doing, it hides the misfit. Right? One thing we saw in this class with fitting models of data. When you have low degrees of freedom, it's a lot easier to get a model to fit. Those degrees of freedom come from the number of covariances in the observed data. So my friend in my example I was telling you about, my friend's birthday today, I won't tell you who my friend is, his birthday today, he had 41 items he made into 10 sums. Right? Hey Siri, what's 41 times 40 divided by 2?
41 times 40 divided by 2 is 820.
That would be the number of covariances in the covariance matrix if you did the same model with all the items. Okay? Hey Siri, what's 10 times 9 divided by 2?
10 times 9 divided by 2 is 45.
Okay. So your degrees of freedom in the big model is 820. Your degrees of freedom in the small model is 45, or minus the number of parameters. Okay? Which one do you think might be easier to fit your data to? The 45. Right? Basically, I look at degrees of freedom and model fit. Model fit is sort of stretching parameters to try to reach all of the covariances. And it's a lot easier to stretch in 45 directions than it is 820. Right? So that's what I'm thinking about. So parceling, we can use the same approach I'm about to show you in parceling as well. You can build a simultaneous model that takes the place of the parcel, but keeps the items. All right. Here's where error can come in some scores too. We have measurement error. It's clearly right there, but there are other places for error as well. We could misspecify the number of dimensions. If you have a multidimensional assessment, and you sum all the items into one score, that one score is going to be off in certain ways as well too, even though it's a projection too. We could make constraints on parameters. I haven't talked about parameters yet. That's going to be some error. There could be a functional misspecification. What if the factor model, all of our factor models look like this? What if there was a quadratic term? What if we forgot about this? Like that. There's nothing that says that. It could be a nonlinear relationship as well, right? All that could be there. We could be misspecifying the outcome distribution. What do I mean by that? You're going to see this in just a few minutes. If we have a binary item, and we put it in a model that looks like this, it's not going to go well. It'll go, probably not well. Right? That actually is part of the problem of having some for just a moment. Although you're like, wait, there's no outcome. What if we just add things up? We'll see. We could also misspecify the distribution factor, missing data error. Although we don't have a lot of sampling error in the sum score, except for the number of items is short. The sum score is the sum score. So why does error matter? I just mentioned that before. We could have bias estimates in secondary analysis. So our point estimates of coefficients that apply to that model that use coefficients. We also bias standard errors as well. In fact, I mentioned this. Basically, we know this bias estimate would be like the regression slope, and this would be the standard error of the regression slope. And we know the Wald test is roughly equal to beta over the standard error of beta, right? So you know what happens if this gets smaller or faster than that, the z test goes up. So when it comes to significance, if we're not in a large-scale testing world, if we're in a research world and we're worried about p-values, this is bad for p-values. In fact, we have this idea, if you heard of the replication crisis, where studies wouldn't be able to be replicated. A lot of them, there's tons of websites, people have gotten in trouble for mishandling science. Anyway, long story short, it's good to be worried about, but I think when it comes to a lot of what we do with psychometrics, I think we might be behind some of the problem with that. So we tell you how to do this, get the score, but we won't tell you what to do with it when you've got it after. Now, some people have, but it's not well known, not well practiced. And in fact, Bruno Zumbo had an article in 2013 that sort of suggests this as well. I've always thought that if we tried to calculate that based on psychometrics, we would see that the standard error gets smaller faster, so the p-value is more likely to be significant when we use secondary analysis. But I'm not there yet. I don't know. I'm not making that as a thought, not as an actual claim. Does that make sense? A low confidence thought? I think I can prove it, but I don't want to. Anyway. Some sources of error matter more than others, but the key I want you to remember, if nobody says it in this class, every time you get a theta, every time you give somebody a score, don't forget the error. It kills me when I read a score report, and there's no error in it. And I'm like, but people don't understand the scores. True. However, if you have a computerized adaptive assessment, you may have different amounts of error for the same score. Usually not. You try to minimize, you try to make the same error. If you have a non-computerized adaptive assessment, you have widely different errors based on score, right? So that's bad. I can see why people would not want to report the error with the score. Because that's like saying, especially if you're paying for that score. I like to say the word selling betas, that was the thing last fall. If you're selling the betas, you want to tell people, hey, by the way, this beta sucks. But that's what happens. Anyway. So let's talk about factor scores for a bit. Here's our CFA model. Factor scores where F happens to D. I mentioned about indeterminacy in class. There's indeterminacy because we're not precisely estimated. There are also indeterminacies we saw because you can parameterize factors differently. You can have different structures leading to the same results, right? Like rotation and so forth. But here is our psychometric. I kept this slide from back then because I liked it as positive. Here's our latent trait score. Let's imagine we have three singers These were popular people back in the day. Let's imagine this is just I don't know what trait this is. Singing ability, mathematics, psychometric ability. Who knew Taylor Swift knows IRT? You never know. Anyway. Those were provided by my daughter when she was little. That's her right there. But the key in thinking about these scores is if you just look at the score, we have an order. We talked about this as an interval scale. Right? How many times have we heard theta is an interval scale? I've said it, right? But that's neglecting the fact that there's some error in each. So if you think about what the error, what's the error telling us about each theta? It's telling us, this might be the most likely score, or maybe even the average of the scores that are possible for this person. Most likely being maximum likelihood, or MAP. The average being EAP, of possible scores for this person. These are terms that we can connect to things that we talked about in class. But if we were to compare Miley Cyrus and Taylor Swift, what could we tell about them? We could say that it's likely that Taylor Swift has more ability or more of the score than Miley Cyrus. But it's not certain. Right? And that is where we can say the following. The other thing we could also say is, now technically we know these normal distributions extend to infinity on either direction. So there is a small, very small chance that Justin Bieber may overlap. But we all know Justin Bieber first. But second, let's disregard that overlap for a little bit, because it's really tiny the way I tried to draw this, right? We could say almost certainly that Miley Cyrus or Taylor Swift has more of the score than Justin Bieber. So if we were really taking score on this, Taylor Swift and Miley Cyrus, we don't know, right? They overlap. We think Swift's higher, but we don't know. And then there's Bieber over here, right? So we could say that something like that, right? This is called a weak ordering. So when you consider what the scores might actually be when you consider order, it's really no longer an interval scale anymore. Because an interval scale would only look at the point estimates of theta. Right? An interval scale would say Swift has more than Cyrus, and both of those have more than Bieber. But really what I'm saying is once we consider error, it becomes less certain. And that's what we call a weak order. There's a whole field of axiomatic measurement where you can get into orderings and weak orders. And this was really big. There were some really interesting, influential papers in the 60s and 70s about sort of orders and scores and so forth like that. You can get into a little bit of that if you want to have some references, let me know. But because of error, really, it's sort of like this, right? Now compare that with something like this. We have little error. Now we have much more of a stronger order. And let me also go a step further. What happens to these distributions is the number of items go up if the model fits, a unidimensional model fits. As items goes to infinity, the standard error goes to zero, right? Particularly if we're using maximum likelihood, this would basically show asymptotically that the point estimate score converges to true value, right? Asymptotic consistency, right? So there we have it. So factor scores provide a weak ordering of people. A different version of this factor model. So if we identified it differently. So we talked about this when we were looking at the notation for the last item, how the factor variance was estimated because we had a marker item H. Maybe you don't like the marker item. Maybe I used a marker item and you used standardized factor. The value on the x-axis would change for theta, but the order of scores would not change. And the relative width of each of the distributions would also not change in that sense, right? So when we get, regardless of how we identify the model, we get the same ordering people, and we get the same error relative to the metric that is provided, right? Am I saying anything wrong? Call me out when I'm wrong. Do it. I need to fix it. I'm wrong a lot. Warning you. And there may be wrong things in here too. Okay? How we doing? Let's just check. Have I said anything that does not fit with what you know so far? Cool. Okay. So let's point this out. This quote from 2015. Sorry. So factor scores in CFA, we talked about this, are found using the same methods that we do in IRT or everything else, right? Either maximum likelihood or Bayesian. We have our likelihood function, we can calculate a score. It works. The only difference between test scores and factor scores, some scores and factor scores is the distribution, in this case, and the only difference between CFA and IRT is the assumption of the date that we talked about. That's why I have two examples here. I did take this quote. Found this in 2015. There was a professor at University of Texas named Walter Stroop that was, I want to say, unhappy with how Pearson was doing the state assessment and test Texas, and became somewhat prominent. Pearson actually sued him. Anyway, Pearson and Dow used to, I don't know if they still do, used to endow a chair at UT Austin, like in their version of our program. But here's what I took this from this link, which is no longer available, by the way. So you have to take their word for it. I went to these slides in 2015. IRT does not rank order students and select test questions. Let's see what you think about it. Let me just give you, this is written by one of our vendors. Y'all are students of the industry. I want to see a thumbs up or thumbs down. When I read a sentence, if you agree or disagree with what's written. Ready? IRT does not rank order students and select test questions. Thumbs up, thumbs down. It's interesting because I feel like the meaning of it, like IRT itself is a model. So yeah, I guess you could say the model isn't doing any of that. But what we get from the model is a rank order of students, and we often turn that model to use test questions. So, okay. IRT simply measures students' academics and knowledge on a scale like a ruler. Let's start with a ruler. How do you feel about that analogy? Thumbs up, thumbs down? What? A ruler, if I'm looking at a ruler, if I'm going to be exact with the first sentence, I'm going to be exact with the second. A ruler has a fixed 0 point. Do we have that in IRT? When we measure, a ruler measures on a scale, but a ruler has a fixed 0. A ruler, when I measure this iPad and it's 10.9 inches, and I look at my screen and it's 20.8, 21.8, I can make the claim that my screen is twice as big. Because a ruler provides measures on an ratio type scale. There's a fixed 0 point. Where's the fixed 0 in IRT? Okay. So what's that? No error. That's right. Also no error. Yeah, the measurement error of the ruler is usually the measurement error of the eyes of the person using, right? So, yeah. Okay, are we good so far? What's your impression of this so far? Please don't write this on the field. Not buying what they're selling. When students increase their knowledge and skills, their test scores will increase. I would argue yes. I'm going to give you a thumbs up on that one, so long as the test measures what was increased. Yes. And let's assume this is. IRT provides a thorough and fair measurement of growth and mastery. Wow, this guy IRT telling you this thing sounds amazing. Not what I know. What's that? No, this is from Pearson in their response to Stroop. Yes. Yes. This came from Pearson. This is Pearson putting this out. At the time, I believe Pearson was the vendor for the state contracts for the accountability assessments tests. That's a huge contract. Right? If we're talking, and I'm on the low end here, but if you think $20 a student for a cost, and think of the size of Texas, which is the second biggest state in the country. I think at the time was second biggest, and New York sort of got passed by them. Right? Think of how many millions of dollars the contract was worth. And so Pearson was trying to keep the contract, from what I understand. Or better yet, didn't felt like I don't remember what Stroop's argument was. I actually don't. When I read his, I was not really impressed with his argument either. I was both of you were wrong on this. So I'm not going with that. But when I see this, can you take that apart? Is that right? Anyway, I just thought I'm making this my case that when we're in industry, when you're in industry, if you take a job in industry, or if your RA is for selling datas, this might be what you're doing and you don't even realize, right? There's a lot of like, oh, you wouldn't understand, so we're just not going to tell you. In fact, we're going to bend the truth, or we're going to put a marketing spin on things, and that's the best thing. I'm not saying it's false. Some parts are true. What do you think of it? When I saw that, I had to put it somewhere back then. I still find it pointless.
There's a really good article called PTAC on Sex Nutrition by Bruce. That kind of talks about the truth that they of sex psychologists gets if I kind of did this as well. It's just, it's interesting to think about relationships. It's so true, even that's relationship about sex.
Oh, it's going to happen. And, there are good people who work at Pearson, and there are good things that Pearson does. So I'm not going to bemoan Pearson's nonsense at all. Right? So let me just say that. Don't sue me. Okay? I'm not making claims. But that being said, I can see how an organization might let this happen. Because the person responding to this may not be the person who understands data, right? Or understands IRT. And then when you go a step further and you involve the marketing folks. Have you seen the marketing when we do at the university? Wow, we're amazing. All right? So it's marketing, honestly, I swear, I wonder if I've never taken a business class, but I feel like some of the marketing I read, I'm like, is one of your classes how to lie? And the other one, how to lie and sound really good? Because I feel like that's sort of, like how to lie but not actually lie. How to get the feeling that comes with the lie, but the words are at least plausibly deniable. Because I feel like that's where it shows up. You know what I'm saying? Like, I'm going to tell you something that is factually either sort of true or can't be proven. And you're going to come away with the feeling that I absolutely, what I was intending to tell you was perceived as the lie. Does that make sense? So no, I didn't say that. You're making that up. Oh. Yes. Right? Anyway. Yes, it is true. It is interesting. So anyway. So factor scores, they go by different names. We've combined them in our program. Lisa and I combined them, and this is my teaching. Sort of introduce them interchangeably, whether you're using CFA or IRT, that's it. But there is a big distinction between the two that you'll see as you go out there. There has been a historical relationship between exploratory factor analysis and scores. So in the beginning of psychometrics, all we had was EFA, and all we were doing were about rotations. Yeah, there was a problem. There were a ton of methods that were tied to EFA as factor scores in EFA. That's a nasty problem. And by EFA, I mean the principal components derive EFA. So the matrix decomposition approach, not the lower echelon version that we do in our classes. We're only focused on factor scores that are using the posterior distribution. We use Bayesian versions of factor scores. Most of this would be true for ML as well. The only difference would be the upper and lower end would have to be defined. The all correct, all incorrect would have to go and set a score for. But apart from that, everything holds. These are identical methods. If you really want to get into it, there's a book by Lawley and Maxwell, 1971. I like that book. I would never use it now, but from a historical perspective. Bartlett scores, sometimes called this, that dates back to 1936. Ironically, if you go over the stat department, if you go to biostatistics, and you're doing mixed models, we will also call these best linear unbiased predictors, BLUPs. Anybody even ever talked about a BLUP before? When you talk about mixed models or multi-level models, the random coefficients, when we estimate those, are factor scores, effectively. They may not have a loading multiplying them, but neither does some of the psychometric models we have. Sometimes they multiply a constant. That would be a random slope. The methods they use are the same. Best linear unbiased predictors, and that's because they're Bayesian. That's to distinguish them from the fixed effects in a model, which sometimes goes by blue, or best linear unbiased tests. So it's an interesting world. What I'm trying to establish here is if you understand a lot of methodology, right, cross disciplines, there's a common understanding of what these scores have to be. All right. So the factor scores are our estimate of our person's unobserved trait, and because we're not measuring the latent variable directly, it's really a missing piece of missing data. One way of looking at it. Right? The classical test theory notion is not that way. In classical test theory, we have the sum of the items, the end. What's missing about it? Who cares? The sum. Sum is observed. Right? It's only when we start to say the sum is a proxy for the true score that we say that that sum is really an estimate. Right? So in missing data, the key in missing data, when I started my life in college, like my second year, I was in a research methods class in community college in psychology, and we had to use SPSS. And SPSS back then had a thing with missing the missing data module was like that was their marketing in the mid-90s. Missing data. You know what that was? First option? Mean imputation. You got to call in the data, someone's missing a value, take the mean of the variable, put it in there. Come to find out, that's pretty bad. Why is that bad? Because all the missing becomes the mean. And there's no error around it. Right? So a lot of missing data boils down to the idea of you don't know what the missing would be. So you have to come up with a range of values for what it might be, and you have to preserve that range of values as you move forward in other analyses, the distribution for it. Cool? That's the key. There's lots of ways of doing that, but that's the main thing. So, each factor score has a distribution of possible values. The mean of that distribution is often used as the factor score itself, sometimes the mode. MAP versus ZAP, and depending on your assessment, there could be a lot of error in that distribution. Therefore, the use of factor scores must reflect the score is not known and follows the distribution. So if we're going to use a factor score somewhere else, let's do it. Here's our factor score distributions. We mentioned EAP and MAP. These are kind of examples. MAP and EAP converge in a normal distribution. Turns out, in factor analysis, when your error is normal and your factors are normal, your factor scores follow a normal distribution. So you will not hear the words MAP and EAP in factor analysis to get a point estimate of the latent variable because they're the same. The maximum and the expected value are identical. However, that's not always the case. This is not actually a posterior variable, latent variable distribution, although I'm guessing you could find that. But think of this, the factor scores, let's take either the Bayesian version or the maximum likelihood version of those. As the number of items goes to infinity, we can say some things about them through maximum likelihood theory. Right? We can say that they converge in distribution to a normal distribution. They converge into their true value as n goes to infinity. And the variance goes to zero, right? Asymptotic normality, asymptotic consistency, asymptotic efficiency, or relative efficiency, or asymptotic consistency. So this could be what your factor score for theta looks like with a 5-item assessment. But as the number of items goes to infinity, you're guaranteed, who knows when infinity happens, but your factor score distribution becomes normal. Right? So if you think about it, how many of you have used any type of method that assumes normality of factor scores? Or normality of something. I was on a student proposal defense few weeks ago, and that came up. So that is an assumption. You have to assume the test is long enough, and the model fits to make that assumption. That's all. Not a big deal. There's ways of summarizing variance. If you're in the EAP, you take the expected value, and you take the variance of the distribution. If you're in the MAP, you got the maximum, and you have a variance based on Fisher's equation. Right? So you've seen that before. Let's tie factor scores to classical test theory. Or more importantly, factor scores to, let's put a line through the sum scores. Okay? So in classical test theory, we know this, y equals true score plus error, for that reliability. You have the variance of all this here. Therefore, the reliability of factor scores can be computed using model estimated parameters. The big caution about reliability in this case, and this is not a conditional reliability, first of all, so we know that that's probably going to be wrong. But the other one is that the model must fit the data. In this case, unidimensional model. Right? And we're going to soon see that the reliability can actually be estimated by CFA model. But let's keep going. Factor scores are empirical based estimates. That means there is a prior distribution present. That prior distribution may have parameters that are estimated. Empirical based talks about putting prior distributions whose hyperparameters are on data. Those hyperparameters often get estimated. In CFA, that'd be like the case where we estimate the variance of a factor. How can we estimate the variance of a factor? Set one loading to one, a marker item. That's an empirical based version of a factor score. But there is a prior that goes with it as well. Often you'll see ML estimates, frequently estimated. I mentioned this before. Those are MAP Bayesian methods without the prior. And the other caveat will be there has to be an artificial choice of what the maximum and minimum score will be, the ceiling floor. Because those patterns, particularly in binary data, right? Somebody who's correct on all items, you can show that the likelihood function for theta is forever increasing as theta goes to infinity. Right? There's no upper end to it. All right. You know, Bayes' theorem, more Bayes' theorem. You want to see how we get CFA scores? I think I've shown that to you. I'll go quick. But there's Bayes' theorem. This is Bayes' theorem put into factor analysis. We're after the distribution of the score is conditional on the data. Right? So that means we need the distribution of the data conditional on the scores times the distribution of the scores over the distribution of the data. Right? This is our model. This is our prior. And this involves an integral. Right? Integration the numerator. So here's our model. So here's our distribution for a single factor, our distribution of the data. And for multidimensional factors, that looks like that. The distribution of the factor is normal. I just left the mean and variance in. Oftentimes we have to estimate them, and you don't have to fix them. That's okay. And then now what we can say is this. We mentioned in class the target distribution for CFA, model fit, was a we had to go derive what that was. It was multivariate normal. So we actually know what the distribution of data happens to be in CFA. It's multivariate normal, where the mean vector is given by the mean of all the items is given by, by the way, the distribution of the items, the mean of the items is given by your multivariate factor model there. And the covariance matrix is lambda phi lambda transpose plus psi. Remember that? That was like core. This is the classic formula. That formula right there for covariance in your factor model shows up 1. I'm using it again here. Okay. Another reminder about distributions. This is a conditional distribution up here. Right? We can show a conditional distribution of z given x is really equal to f of z and x, the joint distribution divided by marginal. And if you do some rearranging with algebra here, that looks like right there. This is the conditional distribution of z given x. So we know that we need that too, right? So what does that mean? That numerator at the top right here of Bayes' theorem could be re-expressed as the joint distribution of y with our factors if we had observed our factors in the first place. I'm going to use that result because multivariate normal distributions make it easy to figure out what things happen to be. Right? So if a set of data x is multivariate normal, then we can say the conditional distributions of x are also multivariate normal. Those of you in math stat probably have shown this in places. What do I mean by that? If theta 1, theta 2, theta 3, they're multivariate normal. What's the distribution of theta 1 conditional on theta 2 and theta 3? Univariate normal. We can show that. And we can actually derive what mean should be and what variance should be based on properties of multivariate statistics. So we can show the distribution of the data, the joint distribution of the data is multivariate normal. Then we can use the result coming up to show that our posterior distribution of factor scores is also multivariate normal. That's where I'm going with this. I'm just giving you more of the math because I want to keep this my one last chance. What do I mean by that? Here. Let's imagine we're looking for the distribution of x1 conditional on x2. Maybe this is, like I said, theta 1, this is theta 2, and theta 3. But they're vectors. They can be any number either on either side, 1 or 10. Doesn't make a difference. 1 around, whatever. We can do a similar partition to mean vector, and we can partition to covariance matrix. Right? So we have a mean vector 1, mean vector 2. Those are the two partitions. And then the four different versions of the covariance matrix. I will say that sigma 1, 2 is equal to sigma 2, 1 transpose. Right? This upper part is the transpose of this lower part of the diagonal matrix. Right? So if that's the case, in multivariate normal land, even Wikipedia will tell you, the distribution of x1 conditional on x2 follows the normal distribution, where the mean vector follows this function right here. Right? What is that? The mean of the condition upon variables, the upper right triangle of the covariance matrix, the bottom right triangle, the bottom corner are observed values of x2 and the mean for x2. And if you believe me, if you go back to the scalar equation for this is linear regression right here. Believe it or not. That is linear regression happening in front of your eyes. It's crazy. You get that in a regression class. We also know the covariance matrix comes from this form, where it's the upper left triangle of the covariance matrix minus the product of this times that times that. Right? And actually this is inverse anyway. So there's our distribution up here. This is the distribution of the observed data. This is its mean vector. This is the mean of our factor scores. This is the covariance matrix of the observed vector. This is the covariance matrix of the factor scores. And this is the cross product of covariance between observed and factor scores. So with all that in hand, you can tell me, I can tell you that for any given values of y, the mean of that distribution of factor scores is given by this long algebra function, which plugs in these values to those equations over here. And the covariance matrix is this, given by the values of the covariance matrix using the equations before as well. So it's knowledge of what the factor model is and knowledge of multivariate normal distribution, you can come up with the distribution of factor scores. That's all I'm doing this to tell you is the CFA, we know what that is, right? In IRT, that's very difficult, but we can. And I made this hashtag before. You can use that if you like. In fact, if you search what used to be Twitter, you'll see people using that over the years. Just stay off social media. Don't be social. Be like me. Just be with code and data and books. My life is wonderful. I'm just kidding. Just kidding. Anyway, what does that mean, though? When using measurement models and assuming multivariate normal data and normally distributed factor scores, the posterior distribution of factor scores are multivariate normal. And you know that means the MAP and EAP will align. Because the mean of that distribution, and the mean, the expected value, and the mode, being the maximum, are identical. And not only that, the factor score is the function of the model parameter estimates. Right? If you go back to this slide here, our factor scores, the mean and the variance, are purely made up of model parameters. right? Loadings, intercepts, covariance amongst factors. Unique variance. Cool? Excellent. All right, now we're going to link these together. So, some scores turn out to have a correlation of 1 with factor scores. When factor scores come from a parallel items model. You've heard parallel items. You heard it in theory and technique. What is it? The definition of parallel items. Parallel forms, because items don't matter. Equal mean, equal variance, equal covariance. Beautiful. You pass. Tell Dr. Lee. You've passed. I don't even know if you've taken the class before. You've taken it before. You probably passed it. Anyway, we can do the same in the CFA world, where we come up with items such that the items have the same mean. So each item has the same mean. Each item has the same variance. And each item has the same covariance. Right? So remember what the CFA model told us about what the item mean should be? Right? If I standardize my factor, let's just make it easy. I don't have to, but if I did, then the mean of each item is the intercept. So if every item has the same intercept, I have a parallel items model. Every item means the same. Equal variance. What is the variance of items in this situation? Well, it's lambda times the variance, lambda squared times the variance of factor, which is 1, plus psi squared, the unique variance right here. So that means if all the lambdas are identical, and all the psi squareds are identical, then all of the variances of each item will be identical. Now, I don't know if you remember the formula for covariance, but it turns out the covariance for any pair of items is lambda for the first item times lambda for the second item. Let's call it I and J. But I just said all the lambdas should be identical, so when they're all identical, all this becomes lambda times lambda, and it's the same covariance. So what you just said, I've built a model for. Sounds pretty good, right? If I estimate that model, there's the Lavon code for it. If I output the factor scores using the predict function, and I take the factor scores on the y-axis, or the x-axis, take the sum score on the y-axis, I get a perfect correlation. And that's the correlation of 1. That's not even approximate. That is so perfect, it has 1 with no decimal places. What do you think about that? When I started this lecture back in 2015, I used tau equivalent as Hong as you mentioned, because I've been told some scores tau equivalent. No. I'll show you tau equivalent in just a moment. Now, I did this for the binary items. So I did CFA with binary item responses. Are there like flashing lights and alarms in your head going off? Wait a minute, Tim, you did what? Yeah, I did. And when I did that, here's the score of, here's the sum score. Here's a 0, a 1, a 2, and a 3. That's the observed. And look at my correlation again. At 1. So if someone says to you, what is the model behind classical test theory? To me, now the scale is off. Turns out Dan Nish had a paper a few years ago showing how you could actually go and configure this to have the same number of parameters, but you can scale right. You can figure out how to do that. I will say my lecture came first. But still, this implies to me that if the scores are the same, and the score is the only thing you get out of classical test theory, then I'm going to deduce that the model that underlies classical test theory is this: a parallel items confirmatory factor analysis model. A model where all item intercepts are equal, all loadings are equal, and all unique variances are equal. A 3-parameter model, whether I have 3 items, whether I have 100 items, just 3 parameters. So if I were in theory and technique, or teaching that class, I'd start with this, and I'd be like, can you test this hypothesis? Because one of the things that we talk about in theory and technique is, well, I don't know if you talked about it there, but we talked about in our class, assumptions, unidimensionality. If we're in a CFA framework, can you test multiple dimensions? I hope you learned that in this class. Yes. Can you test whether you should be adding items up? Yes. Right? Can you test if this model holds? Yes. So every time you add items up and you don't test this, is that a good practice methodologically? The question you need to ask yourself. Because that's what's happening. You believe me. I'm trying to make you believe. I'm trying to earn your trust here. And scientifically, I'm trying to give you the evidence to suggest that this is the only option that have. Anybody disagree? Anybody on Zoom disagree? Watching you guys. I don't see disagreement. All right. We can also look at this. I have this for different scores. This is the liquid items. The liquid scores, a lot more scores than liquid items, right? If every atom has six possible scores, here we've got 6 times 6 times 6. I don't even know what that is, 96 or something. 18 times 6, what's that? 108, right? Sorry?
18 times 6.
6. 18 times 6, 108, I think. Maybe not. I don't know. My math is bad. Yeah, I think 108. Anyway, I picked a few at random. Just showed here. This sum score is 4. That's because the person had a 1, and a 2. That's their score. Here's the person with a 1, a 2, and a 1. The same score house, right? You can see it. All that matters is the score. But let's look at this with the binary data. Here there's only 4 sum scores. 0, 1, 2, or 3. Here's the 0. Right here. Right? Here's the 1. They're all the same. Here's the 2, and here's 3. Right there. So we've got them all the same. Where have you heard in other psychometric contexts that the sum score, kind of like a proxy for a latent variable, not classical test theory, but in other places? Perhaps you heard it in Roche model, or one parameter. There's an estimation method that's enabled there called conditional maximum likelihood, where we can substitute latent variable estimate, the sum score, or some version of that sum score. Have you heard of that before? Statistic. That's correct. The difference between Roche, or that one parameter model, and what we have here comes down to looking at this plot, and our theta estimates start to have a curve to them. And that's because as you get toward the maximum, the logit for each of the items shifts the response, the theta. It sort of suppresses what theta is, right? The maximum probability can only be close to 1. Right? It can be 1, and then the composition shifts. All right. Have I earned your trust on this so far? What do you think? Have you seen that result? Have you ever talked about that for a sum score? So now, when I put the context of the problem next week together, and Lexi said, hey, I've got 4 thetas, let's just add, and you said, let's weight them together and add them up. That's like saying, I'm going to make a single factor model of my thetas. And maybe that's sufficient, maybe it's not. But that's interesting. Whenever you see a thumb, so excited. Making fun of myself. My goodness. Whenever you see a sum score, I'm all fired up with this. Substitute the parallel items model for it. You can't. So that's the main thing. Before we get too far, though, we got to check model fit. This model fit, RMSEA. This is robust. Probably pretty good. By the way, in a 3-item CFA model, I tell you that's just identified, right? But if you put these constraints on it, where all the loadings are equal, all the means are equal, and all the variances are equal, you have degrees of freedom left over now. And that allows you to do model fit. So I'd go to theory and technique, and I'd teach you this first. And I'd be like, does the model fit the data? Well, the p-value for it's actually no, but approximate maybe. Right. But if you're thinking about it, if you're in an assessment program that does this to provide scores, to me, this goes in your technical manual. This is the validity of the evidence that you really want, right here. Right? Because if I'm giving you a sum score or some scaled version of it, I need to establish that that's appropriate. All right, let's go on with. We can show factor. You want to see how we can factor score reliability with this? What's the reliability of this factor? Well, we need the variance of the factor plus the variance of the factor times the standard error of the factor. Turns out in factor analysis, the standard error of the factor is constant. Right? That's why we can't create computerized adaptive assessments that rely on CFA models. Because there's item information, the thing that calculates this, is constant. Right? An item contributes the same to each factor, regardless of what the value of the factor is. It's the big difference between CFA and IRT. In IRT, there's an information function. Right? Item information. And that item information in binary items usually has a single peak. And we can say these items are more informative for this value of theta, these items are more informative for that value of theta. The flip of all that is that the information is usually far lower than the information in a continuous data approach. But so CFA, we can do this. Turns out we can actually calculate the factor score reliability. You can go do that yourself. I can also do this. Let me derive this. This is a contribution by Rod McDonald many years ago, but I think this is really important. So in classical test theory, unit analysis is the sum score, the sum of the items. Or this is the model. Y is true score plus error. And in a CFA, it's this, each item. But we can come up with a person's total score by just taking their sum, right? Sounds plausible. So let's do that. And let's substitute the model for y. Right? Because that's the model is what we're assuming. When we do that, here's our sum. Now we can distribute the sum across different parts. And we can map these parts into two sections. Clearly this is error. Right? This right here. Right? So that's error. All this must be true score. Right? So now we have something that represents the true score for each person, and something that represents the error for each person. Why don't we calculate the variance for both? This is where your mathematical statistics brains are going to get fried a little bit, but we can do that. Okay? If the true score is this right here, and error is that right there, then the variance of true score, we can actually separate this. What's the variance of a constant? 0. It's a constant. In this case, mu is a constant. What's the variance of lambda squared? Well, in this case, it's treated as a frequentist estimate. It's a constant as well. But it's multiplying a random variable. I set that the variance of the factor is actually sigma squared f. And it's this constant squared times that factor. But we can calculate it. The same thing with the variance of error. If we have no correlated residuals, which we have to assume in a parallel items model, then the variance of error is the variance of this, which is the sum of those variances, some of the unique variances. So it turns out we can use IRT or CFA parameters to calculate reliability coefficients as well too. Right? So here, the variance of true score, the variance of true score, and the variance of error. And I can do this within Levon using these defined parameters right here. Which you know what that makes me so happy. It gives me a standard error for the reliability. Yeah, that's what I want. I mean, how many times have you had that standard error reliability? Ha! Take that theory and technique. Just kidding. What is that? 0.629, and that's standard error. 0.025. So the reliability for this assessment is 0.629. 3 items. Not good reliability. That's what it is. Turns out that reliability has a name. You probably heard of it before. That's the Spearman-Brown reliability. And I just estimated it with CFA model. So I'm basically taking you through a tour of all the classical test theory stuff. This is sort of part of the reason I'm like, classical test theory. We can do that with CFA. Okay? Anybody seen that before? Lisa try. I think Lisa talks about it a little bit. I go over it on it. So, Spearman-Brown. What year was Spearman-Brown? What's that? Like 1919, 1920? It's like women didn't vote in this country back then, right? That's the perspective we give you, right? Yeah. What we end up doing after that, where we get to tau equivalent, is sort of we recognize in Spearman-Brown the assumptions of parallel items and parallels, right? That's an overly strict assumption. One way of weakening that is to effectively say that covariances may vary across the items. That's where tau equivalent comes in. And if the covariances may vary across items, that might be where we allow for a different factor loading for each item. So in this case, the tau equivalent items, this is the parallel items. Hold on here. The factor loading should be like this. It should be lambda 1, lambda 3, and lambda 5. Sorry for the type there. The notation should be the same. I was drilled in my dissertation defense about notation. I hate it when I'm wrong, because that was such a horrible thing, but I'm grateful to the professor. The professors that helped, Larry Hubert in particular. Larry Hubert would always tell me, in real estate, the three most important words are location. Anything statistical, the three most important words are notation. Bad notation. Here is the tau equivalent model. The model fit for it. Looks like it fits better. Should fit better. Here is the correlation between the sum score and the factor score. It's really close in this case, and that's because we have 3 items. Actually, most of the time we'll be very close. But take a look at what that implies. I'm going to dwell on this for a little bit here. Right? If you take the person's sum score, let's say everybody who had a 10. Actually, let's take 9 right here. This right here. And let's imagine you need to score a true score right there to get into grad school. Right? What does that mean about 9 and 10? Well, when you see this, what ends up happening is you get sort of reverse ordering. All these people would have the same true score, the same sum score, but their latent variable score can vary. And you may reverse the ordering. And look at this. Here's the people who had a 10. Here's the people who had a 9. There's a segment where they be reversed. Right? So that may not bother you much because the correlation is so high, but if you're one of those people and you didn't go to grad school, or you weren't able to practice medicine or nursing or whatever, that can be a problem. Right? It gets worse when the model doesn't fit. But that's what's happening. This is another comparison of the two. This is what the score would be under tau equivalent. Here's the parallel items themselves. And then I didn't mention. By the way, this is the loading squared over unique variance is item information in a standardized factor CSA model. Unidimensional CSA model. Reliability is a little bit higher for factor scores. Yada yada yada. But this number right here, actually 0.620, using the same formula to calculate reliability. This is Cronbach's alpha or Gutman lambda 6. It's the same thing. So we just see a for that. And then finally, if you want to estimate everything uniquely, that fits the best. Still has a big correlation, but you'll see there's even more factor scores. You still have that overlap. And the coefficient of reliability there sometimes gets attributed to Rod McDonald's and Mega, they call that. But what does that reliability represent? It's reliability for some of items under this model. It's not a reliability for the factor score. It's a reliability for some score. Anyway, I think that's it. Let's stop there. What I really want to achieve, if you want to see how we can use secondary analyses, I have another example where I'm predicting the latent variable with it. I'm going to keep going just a little bit. But I wanted to show this right here. If I did this in a structural equation model, my standardized estimate of that prediction, when I predict theta from an auxiliary variable, is 0.5466. If I did that with the sum score, it now becomes 0.416. Now, if I did that with the factor score, it's 0.311. That's the attenuation talking about. Beta goes small. Right? Take a look at the standard errors. Right? They also get smaller. Right. And the question is, do these go smaller or faster than these? I don't know the answer. But they're different. Very different. Right? So, point I'm trying to make is that the scores are not observed. Ever. Even in classical test theory, when we sum that score up, as soon as we start to assume it means the true score, that's not observed. Right? The other point I was trying to make is, classical test theory is what? Equivalent to parallel item CFA model. Right? And the math works out. So, now we're to the, is this the penultimate lecture? Is that the one before the last? Did I say that right? I don't know English. Stop with the words. Lecture. This is the second to last lecture in class. Get the English. I feel like I'm trying to aspire to sound better with English, and I realize who cares. Just get the point across, right? For this, think of this when you think about how to handle the problem I phrased that we're going to try to solve next week, which is I need to give an overall score and a set of like an overall higher level score like math, and I need to talk about each of the standards as well. A score for each of those. Because somewhere in there may be the tendency to want to add things up. And if you do that, we added up the standards, although you said it weighted. But if we did, what we'd end up getting, it's like saying, yeah, there may be four standards, but we're going to call it a single factor model. But it's not a very good one. Four. That may be sufficient. Who knows? All right, any questions I want to describe today? Anybody on Zoom? What do you think of it? Have you seen this before? No. Does it change your perspective on summing things up at all? So when I saw this, I was like, hold up, what? I'm going to do what? I didn't realize I was doing that. I'm just adding things together. Well, that's equivalent to the psychometric context that we're used to. And because the light is shining right in the exam's eyes, we should end now so she will not be blinded. All right, thanks everybody. See you again next week. I will have office hours this Friday. So if you need to talk about anything, 9 to 11 on Zoom. Okay? All right. Thank. Oh, pardon me, Vladimir. Vladimir, we will not cover missing data next week. I'm running out of time. I'm sorry. But if you ask nicely enough, I might change my fall class to missing data. Even though I promised myself I wasn't going to prep yet another class while I'm teaching it, I would, just for you. Not just for you, Vladimir, but for the good of everybody. Thank you for pointing that out. Also, want to make one small note before we leave. Friday, big day, we've got GMAS, election for GMAS, and then to end the events of the day, Lexi's going to give a presentation. Thank you, Lexi. No pressure. No pressure. You're going to nail it. It's going to be great. And then I will also note that on Monday, I haven't sent this email out yet. Monday from 10 to 1 or 12 to 1, Alfonso's going to give a practice job talk in this room. I'll have a Zoom link with it as well. You'll see an email as soon as I get my act together later today or tomorrow. Okay? So all are welcome. And if you have feedback for the presenters, absolutely share that in a constructive way so people can get better at presenting. Presenting is like the last thing we can't give you enough of before you head out into the world, but it's so important to be able to communicate what you do. Thanks, everybody. Have a great rest of your week.